Today's lesson in accelerated geometry is section 1.3, creating definitions. So first of all, there's a slide here that says, what is a widget? A widget is something that the book is just making up. It does not exist in geometry. It's not a geometry term. It's just something that they're making up to help you see what a good definition consists of. So they say, okay, here are these made-up widgets over here, and over here we have things that are not widgets. Our book often does that so that you can do some comparison and some contrasting here. It says, what things do all widgets have in common, and what things do widgets have that other figures do not have? So you can look at this and kind of see what's happening. I see inside here that all of these four figures have color on the inside, and this guy over here does not. So I think it has to be filled in with color. And off of the color, I see that there are two of these strings attached. Each of them has two strings attached. Over here, this has two, but this has three. This only has one, so I think it has to be two strings attached. And now if I look at what's on those strings, I see that one of them is kind of a crescent moon, and the other is kind of an eye. Crescent moon and eye, crescent moon and eye, crescent moon and eye. Okay, over here, two crescent moons. This has crescent moon and eye, but remember it's not colored in. Crescent moon and eye. But look at this. They can't have any figures on the inside either, so we just came up with something else there. Okay, so now what am I going to say? A widget is a shape that is filled in with color, no objects inside, just non-white color, with two strings attached. One string has a crescent moon, and one string is kind of like an eye. So then they say, which of these are widgets? Color on the inside, two strings, and a crescent moon and an eye. This one doesn't have the crescent moon and the eye, it just has two crescent moons. This one has a figure on the inside, that's no good. This one has three strings attached, so we can just ignore that one. So the only one that works, that is a widget, is A. So what we were doing is saying, okay, what do we have here? We have a shape, and how is this shape different from all other shapes? And these are all the characteristics that it has that makes a widget be different than all other kinds of non-widgets. So a good definition says it is and you put it into a category. Okay, so a widget is a shape. And then how is that shape different than all others? That has, and then we list all of our characteristics filled in with color, two strings attached, one string has a crescent eye, one has a crescent, one has a crescent moon, and one has an eye. Okay, so now let's do this in geometry, because remember a widget is something they just made up. So here we have a square. So here would be an example of a good definition of a square. A square is, so there is the name of the thing that we're defining. Put it in a category, a four-sided figure. And how is it different from all other four-sided figures? It has all sides equal and all angles of 90 degrees. Now, once we have what we think is a good definition, we have to test it. And we test it with something called a counterexample. So we want to take the definition and see if we can use that definition and come up with a figure that is not what we really wanted to define. So, for example, if I say a square is a figure with four equal sides, okay, some people would say, yeah, that's true, but look, here are some counterexamples. This figure has four equal sides, but it is not a square. This one has four equal sides, but it's not a square. This one has four equal sides, but it is not a square. So to test your definition, try to think of counterexamples that will apply to the definition, that will go along with what the definition says, but that are not when you come up with these examples, not what you really wanted to define. So the steps to create a good definition: classify your term, put it in a category, differentiate your term, how is it different from everything else in that class, and then test your definition by looking for a counter example. So today you're going to be coming up with some definitions of your own, and in that process you should be following these 3 steps. Before we start that, I'll give you some definitions. Parallel lines are lines, that's the category, and how are parallel lines different from all other lines? They're in the same plane and they never intersect. Now in English class, your English teacher would freak out if you use the same word that you're trying to define. I know in English, I know that there are teachers who say you can't do that, but in geometry, that's fine. Parallel lines are lines. You can use the same words. Okay, so here are some examples of parallel lines. Lines in the same plane, that means on the same flat surface, on the same flat screen, okay, that never intersect. And here is the symbol for that. You have those arrowheads. You can have 1 arrowhead on each, 2 arrowheads on each, 3 arrowheads on each, whatever you want. Since these lines are called I and J, we say I is parallel to J, so that's the symbol for that expression. Okay, here are 2 other lines. These are line segments. So this is line segment BA or AB, and this one here is line segment CD or DC. What we're trying to show is that they are parallel, so we put this symbol on here, the arrowhead, and then here is the symbol for that. Line segment AB is parallel to line segment CD. Okay, skew lines. All right, let's go back to these parallel. In the same plane that never intersect. If I take these lines and take them out of the same plane, off of the same flat sheet of paper or the same flat screen, I can have a picture that looks like this. 2 different planes. So this is the top plane, this is the bottom plane. And if I take these lines and make them so they're not parallel but still on that plane, they will also never intersect. So these are called skew lines. They never intersect, but how are they different from parallel lines? They are not on the same plane, non-coplanar. Perpendicular lines are lines, that's the category. How are they different from all other lines? They intersect at 90-degree angles. So I'm sure you already know this from grade school or Sesame Street or whatever. And so here it says this line K and this line L are perpendicular to each other. So K is perpendicular to L. And this symbol, this little red thing in the corner there, shows the perpendicular mark. It just so happens that they put 4 of these perpendicular marks in there and it kind of looks like a square. But in the next example, you can kind of see there is right here the symbol for perpendicular. So this is showing that line AB is perpendicular to line CD. There are 2 lines on the same flat surface and they meet at 90-degree angles. And this is the symbol of how I would do that. Line AB is perpendicular to line CD. Okay, a little bit more complicated now. Vertical angles. 2 angles that are opposite from each other when 2 lines intersect. So here are 2 intersecting lines, here and here. This angle 1 and this angle 2 are opposite from each other when these 2 lines intersect. So angles 1 and 2 are vertical angles. In this drawing, here I have perpendicular lines. They don't have to be perpendicular, but in this case they are. Doesn't matter. There's still 2 lines that intersect, and when the 2 lines intersect, here's an angle 3 and a 4 that are opposite from each other when the lines intersect. So those are vertical angles. Now, if I go back here, I'm trying to get a pen here. This is 5 and 6. They are also vertical angles, and this is 7 and 8. They are also vertical angles. Okay, here it says name the pairs of vertical angles. So they are this one and this one. So then if I change my color, this one and this one. So those are the pairs of vertical angles, and here they're just named with letters. Okay, linear pairs of angles. Two angles that share a common vertex and side, while their two other sides form a straight line. So linear pair of angles are two angles, that's their category. How are they different from all other pairs of angles? They share a common vertex and side, and their other two sides form a straight line. So here's a typical example. Here, this is a line, and here is part of a line. Okay, so it keeps on going here. They just don't show that. They just show this ray part of it. Okay, and what do we have? Two angles. They share a common vertex. So this is angle 1, and this is angle 2. They share this common vertex, and they share this common side, and the other two sides form a straight line. So angles 1 and 2 are a linear pair of angles. They have to be connected to each other. Here's another example, 3 and 4. If I draw in angle 3, it has a vertex here, and those are its two sides. If I draw an angle 4, here's one of its sides, here's its vertex, the same as angle 3's vertex, and it shares this side here. So therefore, angles 3 and 4 are a linear pair of angles because they are two angles. They share this common vertex and this common side here, which is this ray, and these other two sides form a straight line of 180 degrees. Okay, so now name the linear pair of angles here. I'll do it with numbers, even though the answers are going to be in letters. Angles 1 and 2. Angle 2 and angle 3 are another pair of linear pairs of angles. Angle 3 and angle 4 are a linear pair of angles. And angle 1 and angle 4 are a linear pair of angles. And down there I just have them listed with letters. So now in class we're going to do some group work. But if you're at home, if you are absent today or whatever, you are supposed to do page 44 to 45 definitions as stated in steps 1 through 4. So you're going to write a definition along with a sketch of the term. Now if you're at home, you can't send them to me to check or anything, and you can ignore the vertical angles and the linear pairs of angles because we've already done those. So those are in these definitions, but you can ignore those. We're going to do that in class. If you're not in class, you can ignore that last investigation there. Now, if you, at this point, could stop and do those definitions, that would be great. And when you're done, continue with the video. So stop the video now, do those definitions, and then come back and check them, because on the next page I have what you should have come up with. So here's a right angle is an angle whose measure is 90 degrees. An acute angle is an angle whose measure is less than 90 degrees. Obtuse angle is an angle whose measure is greater than 90 degrees. Complementary angles, two angles whose measures have the sum of 90, 60, and 30 add up to be 90. They do not have to be connected to each other, but they could be. Supplementary angles are two angles whose measures have a sum of 180 degrees. They do not have to be connected to each other, but they could be. So if I did that, if this was 50 and this was 130, those two angles would be supplementary angles. And also they are a linear pair of angles because they share this vertex, that common side, and the other sides form a straight line. So those are more definitions that are getting added to the definitions for Chapter 1.